Hey 1005 mathematicians, Mr. Herman here, and this is lesson 5, exercise 4E, and this will be looking at 3D applications of trigonometry. This will be the last lesson for the trigonometry topic. It is one of the trickiest topics, just after bearings, which was exercise 4D. And the reason why is because we want to be able to make sure we get a strong diagram based on context that has been given to us. The learning goal for this topic is to see how trigonometric functions can be used outside the 2D plane and into now the 3D plane. And the success criteria for this topic is to be able to create visual 3D representation diagrams from an explanation and use trigonometric functions to solve for a problem. So we're used to trigonometry being a 2D type topic, because whenever we draw a right angled triangle of some sort, we just see it as this flat image. We have a 90 degree, we have a triangle with 3 sides with a hypotenuse and some type of angle here, and then we solve for one of these sides or one of these angles. But then this triangle can be used in a 3D setting. Now I'm going to try my best to show a representation of this. Let's say, for instance, I were to draw a 3D shape. Now I'm not the best at using the stylus to draw shapes. But right here we have a 3D cube. Let's say I'm drawing it on a 2D plane. But I can already observe 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different forms of right angle triangles from this here. I have to create it myself, but we can look at the flat images of each face. And if I draw a line right here from vertex to vertex, right here I've created 2 different right angle triangles, one here and one here. And yes, they are still a flat version of the triangle, but it's found within a 3D shape. And this is what we mean by the 3D applications part. You can also see one, if I draw a line there, I have a 90 degree here and a 90 degree here. There's another 2, we can do the back face, the side face, top and bottom. But it does not stop there. I can also draw, I'll draw again another 3D shape, like so. This rectangular prism looking a bit flatter. And in this case here, I can actually try to, you gotta use your imagination here, I can technically draw a line at the bottom of this shape, flat line here, okay? So we have this edge or this line going from vertex to vertex, corner to corner on the bottom. So there's one line. I'm then going to draw a line up along the back right spine of this 3D shape. And then to connect the two, from here to there, I've actually created a right angle triangle that can be found within this shape itself. Now it seems kind of abstract that we're going to just obtain a random right angle triangle within here, but you will get context questions that might have this kind of scenario drawn, not to this extent, but somewhat they will give you certain edges or lines that surround this right angle triangle, and you have to use your 3D imagination to be able to draw this, okay? So for now, we're going to look at this example, and it's the only example we'll be looking at, which is found straight into the textbook. This example does have a diagram already drawn in there, but I want to be able to create this diagram from scratch. So that way, when you tackle the questions within the exercise, you can use this method that I'm using here to be able to draw a diagram, because it's the trickiest part of this topic, and also 4D as well, getting that diagram correct from the context that's been provided. So let's have a look at this question here. We have a vertical mast, okay, so another word for mast, so just think of a pole of some sort, and vertical meaning going up from the bottom. Okay, so vertical. Already I've abstracted so much information just from the first 3 words. So a vertical mast is supported at the top by 2 cables reaching from 2 points A and B. All right, let's draw what we do know from that information. So I do know that there is a vertical mast of some sort. All right, so a pole that goes up. That is a terrible pole. Let's try that again. Ooh, that's right. If I hold shift, it draws a straight line. How did I not know this whole time? Oh my goodness. Okay, so we have a mast. Okay, and this vertical mast is supported by 2 different cables. Now, to make this cabling simple, I might draw this in the middle actually. To make this cabling simple, we'll have 2 different cables that reach from the top point. So here's our top. And we've got our first one, that goes here. And our second one that goes here. Okay, and these are the 2 cables reaching from 2 points, and they are supported at the top. This point can be point A, and this point here could be point B. That's all we know so far from what we read. The cable reaching from point A is 36 meters long, so we know that this length here is 36 meters long and is at an angle of 48 degrees to the horizontal. 48 degrees to the horizontal. So we know that this angle created with a flat plane creates an angle of 38 degrees. Now I can draw this line that goes across. It can reach anywhere on this pole. So I might draw my line that looks like that. Okay, even though it doesn't necessarily look like it's hitting the bottom of the pole itself, it's still on this horizontal plane. It's touching the ground. Okay, it's just maybe further down. But what I really care about is the angle that's created with the horizontal from point A. And in this case, it is 48 degrees. Okay, so that there is 48 degrees. And then point B is 24 meters from the base of the mast. So we know that this length here is a bit of a shorter length. I drew it longer, so obviously this is not to scale. But point B is 24 meters from the base of the mast. So we've got 2 different lengths. We've got 36 and 24, and we've been provided with 1 angle. Now, for consistency's sakes, let's just put a line from here to there, and this is a horizontal line created by point B. We don't know what this angle is. I'm not too sure if we even have to find this angle. Let's have a look at what we need to get. The first question is saying we need to find the height of the mast correct to 3 decimal places. So let's keep it consistent. I'm going to get rid of this part. There we go. That might make a bit more sense to you guys now. This is our mast, and we're trying to find what this height is, because we don't know what the height is, and we'll put H for the height. We don't know what the height is, and that's what we're trying to find out. Now we can use 1 or 2 triangles, but before we do, we've got to make sure that we know that that here creates a 90 degree, and that here also creates a 90 degree. So we've got our 90 degree triangles. They're just being drawn almost like at a different angle of some sort. You can view it flat. If I were to take this snapshot and put it to the side, I can draw it flat. Same with this one here, but in the 3D context, you'll see it on a slight angle, okay? And we're trying to find the height, correct to 3 decimal places. We can't really use this side because there's only one side provided and no other angle. So we have to use this side here. We have to use this angle that's been provided here and this hypotenuse, which is opposite the 90 degrees. So let's tackle A. Let's have a look at A. And I'm going to redraw this triangle to see what information we can extract from our diagram. So what I've done is I've taken this triangle and I've just placed it in a better view or perspective. And I'm just going to fill in what I do know. This right here is the 48 degrees. The hypotenuse side, I'll keep it consistent and make it in red, is the 36 meters. And that's all we know. We know the 90 degrees is here. And what we're trying to figure out is what this length is here, because that is the mast. That's the pole that's running up. And again, this is dictated by the letter H. Actually, no. Let's use the letter M, because I don't want to use the letter H to get confused with the hypotenuse. Let's use M. Let's use M for mast. Okay, what do we know? Let's figure out what we do know. We've been provided an angle. So the line of interest, which is what we're trying to figure out, is the opposite side. Alright, so we've got our opposite side of the angle, and we've also got our hypotenuse, which is H. We look for the trigonometric identity that uses O and H. In this case, it is sine. Sine of the angle being O divided by H. And we can go ahead and write this down. Get a black pen again, and we can write the sine. And whatever the angle is, in this case 48 degrees, is equal to O, which is our unknown, so we don't know what O is, that's what we're trying to figure out, divided by our hypotenuse, H, which is 36. Now, remember, when the number is on the denominator on the bottom, you just multiply it by the trigonometric identity. So our M is just going to be equal to 36 times sine 48 degrees. That's going to be our M. So M value, making sure you get your scientific calculator out. You can't do this without it. 36, or you can use a calculator on Google, as long as it has its trigonometric identities. 36 times sine of 48, and this will give us 26 point. Now let's double check how many decimal numbers. Correct to 3 decimal places. So 26.753. 26.753. 26.753. And this is in the context of meters. So our mast height is 26.753, and this is just based on knowing what the length of that cable is and what that angle created by that cable is, which is 48 degrees. And that will be the first part. And I'm assuming that we'll be using this length here to solve for B. Now, before we do that, remember, it's a word question, so therefore we have to answer it in word format. Therefore, and this one's a simple one, the height of the mast, is 26.753 meters. Remember your context, guys, is divided in meters. So we have to answer it in meters. We can't just answer it in centimeters or just leave it as a numerical value by itself. Question B. This question is now asking to find the angle to the horizontal of the cable reaching from point B to 2 decimal places. Find the angle. So there's only 2 angles that's in relation to point B. We already know that this is 90. So it's either this one or this one. They say find the angle to the horizontal. We know the horizontal just means the ground or the flat section of the cable reaching from point B. We are looking for this angle here. Now, even I make mistakes. I've just noticed, I've reread the question again, and I've seen here that I've got some of these 2 facts mixed up. It says the cable reaching from point A is 36 meters long, which is that angle or line there. And point B is 24 meters from the base of the mast, the base of the mast. So it's not that line there, it's actually this line here, 24 meters. So now that we've got this length here, we're going to go ahead and redraw this triangle. Well, not redraw actually, we're going to draw this triangle because we didn't draw it in the first place. We are going to draw this triangle, but in this sense, it will be a bit different. Luckily, this length here didn't affect our first answer, so this is still correct. But what we're looking for is this angle here, provided that we have 24 meters at the bottom, and we also have this height, which has already been given to us, which is 26.753 meters here. This is 90 degrees. All right, let's blitz through this. This is the angle we don't know. This is theta. We have been provided with the opposite of theta and the adjacent of theta. OA is a trigonometric function of tan, and we'll double check that. Over A is tan, so the tan of this unknown angle is equal to the opposite, 26.753 all over 24. We have to use an inverse function if we're trying to look for an angle. So the angle theta is equal to tan inverse. You should hopefully know how to do this from exercise 4b. And it's just a simple tan inverse within our calculator. So let's clear this. Remember, pressing the shift buttan and then tan to get that little -1. That just indicates it's an inverse. Putting it into the fraction form, 26.753 on the top, 24 on the bottom, making sure you click across before you close a bracket, else you'll close a bracket just there, and that will come up as an invalid answer. So the angle created of point B to the horizontal is 48.10. I believe it's 2 decimal places. 2 decimal places. 48.10. So this here is equal to 48.10. And we can just leave that as 48.1 because that 0 after the 0 is a 4. We can write that as 48.10 because that 0 stays unchanged as this is lower than 5. But anything where it has a 0 there, it kind of becomes redundant. So we can just read it as 48.1 degrees. And that is the angle that's been created. Again, we just have to answer this in worded format. Therefore, the angle created, I'm just going to leave it as the angle created, is 48.1 degrees. Now, before I conclude this video, if you were to see this example on the textbook, you will see the answer of 48.11 degrees. And this is because they didn't use 26.753 in the inverse function of tan. They wanted to use the most precise answer because here we just rounded to 3 decimal places. And how we got that 26.753 is through this 36 times sine 48 degrees. So instead of writing 26.753, let's just actually use this equation here within our tan inverse function. So we'll still use shift tan, put the fraction in, but instead of just writing 26.753, which is the rounded version, I'm gonna write the whole version of 36 times sine 48. I'm gonna close that first bracket there. Then I'm gonna go down, and this is still just gonna be over 24. So I've just rewritten the numerator in a more precise way that doesn't indicate any rounding. I'll close that bracket, making sure I go across, press equals, and here we have 48.1 0. Now to 2 decimal places, we look at the number afterwards. This is a 5, which means that that 0 must turn into a 1 here. So this is what the answer in the textbook has provided. Now, either way, if you were to give me 48.1 or 48.11, I will be able to get this or tick this as correct, because it's the skill of knowing which trigonometric identity or inverse identity you need to use. Okay, so my issue isn't necessarily with rounding. However, if you want to be accurate, if you want to be super accurate, even though it's 0.01 of a difference, you would put this, which you've already worked out, into here instead of the rounded version. And this concludes the lesson of 5 exercise 4E 3D applications. What you will need to do from the log sheet is exercise 4E, which is page 293. If you found that the content within here is quite tricky, stick to just questions 1, 2, and 3. They are still tricky in the form of drawing your diagram, but it's very basic of what you need to do. If you're comfortable, 2, 4, 6, 8, and if you want to challenge yourself, every second one from 1 onwards, 1, 3, 5, 7, and also 8 as well. And this concludes not only this lesson, but also the topic for trigonometric applications. We'll probably wrap it up with this one remote learning wise. I don't think there'll be any new videos from me to you guys, because you guys will be starting school soon. So best of luck with this topic. I'll keep you guys posted on what you guys need to do in regards to any type of tests for this topic, and I'll see you guys soon. Bye bye.